Last time, we were deep involved in analyzing a thought experiment, which is designed to help us understand what the underlying description of a quantum state must be, so that we then know upon which basis to build our formal quantum theory. So let's kind of review quickly where we were, and then we can begin to draw conclusions from this analysis. Some of the math here is going to be very important in our conclusion, so it helps to really review it. So you may recall what we had is we had a source that was very far away from a blocking plate that had a certain transmission function. And that source was a source of pure energy, so then at least we know what the magnitude of the momenta of these particles are. And the beauty of this then is that by understanding their direction of travel, we can immediately access their momentum in the x direction, where x is our axis running vertically up the page. We then have prepared a special quantum state of the system with a particular shape, and we could choose any shape that we like. We just happen to choose, for illustrative purposes, a Gaussian shape. And we prepare such a state by having the particles, after they come from the source, pass through a filter that has this particular transmission function, so that then we know basically the probability or intensity of particles after they've passed through that plate. And then that's what we're trying to understand. Their probability distribution in x along the x-axis right after they cross onto it. And also we want to understand the probability distribution of the one other key fundamental quantum variable when we're dealing with simple point particles with no internal structure. Namely, we want to know not only the distribution in positions along the x-axis, but of momenta along the x-axis when they are in this now prepared quantum state after having passed through our filter. So we then went about carrying out the analysis, and the analysis really focuses on the action at one of two different photoplates. One photoplate we simply place, it's a straight plate along the x-axis. We then measure the intensities on that plate, and that tells us the probability distribution associated with our quantum state. We then can remove that photoplate and then insert a large circular or semicircular photoplate, which we then use to record the angles at which the particles travel, and as we've just said, that then tells us what their momenta were along the x-axis. Focusing on the analysis near photoplate 1, we were in the midst of a Huygens wavelet type analysis. We know that we can analyze this situation using traditional optical principles that apply to classical light, because we know from the G.P. Thomson experiment that electrons will show exactly the same probability distributions as photons. So we will just analyze this as we've been trained for standard light diffraction type experiment, and the key to that analysis are these little Huygens wavelets. The idea being that the waves coming in from the source then stimulate each of the different points within our slit, and that stimulation then generates these little wavelets which oscillate up and down with a certain amplitude and a certain phase that may change as a function of x. And then the point is these little wavelets act as point sources. Their waves then spread out and superpose to produce the final diffraction pattern that we see on the far side of the screen. Now, mathematically, to describe each of these wavelets, we need to describe both their amplitude and their phase, and we do this with a single complex number called the complex amplitude, or as we'll see in quantum physics, known as the wave function. And it encodes that information simply as the magnitude of the complex number represents the amplitude of the oscillation of each wavelet, and then the phase, or the angle in the complex plane of the complex number, then represents the actual phase of the corresponding oscillation. We then calculated what these phases and amplitudes must be for our specific example. The phases are determined by a usual diffraction type experiment analysis. We realize that waves that stimulate a wavelet up here at position x along the x-axis have to travel a little bit further, so their phase is advanced relative to the center of the slit. That phase advance then is the excess distance traveled divided by the wavelength, and then times 2 pi radians per full cycle. We then showed using the de Broglie hypothesis that the This evaluates to simply p times sine theta naught, where theta naught was this incoming angle, over Planck's constant times x. And then we notice that, well, p times sine theta, that's great. That physically just represents the x component of these incoming particles along of their momenta along the x-axis. So that momenta along the x-axis then determines the phases, and they are determined via this proportionality constant, which is the x component of that momentum divided by h bar, but we recognize that momentum over Planck's constant is an equivalent way of talking about a wave vector. So we simply define px naught divided by h bar as a constant wave vector k naught, and the particular definition for k naught I've repeated for you here. Very good. So that described then the phase of our complex number. We also had to determine its amplitude. Now, the amplitude is a somewhat subtle issue, but it's not really deep. It has to do with these issues of proportionality, and that we have a couple of different proportionality constants that we have to measure. The first one is the fact that, generally speaking, we associate the brightness or intensity of a wave with the square of the amplitude, with a squared. So maybe I'll write that actually as a squared. Squared, but of course the amplitude squared, we can get that amplitude by simply taking the complex magnitude of our complex number. That gives us the amplitude x, and this brightness then is proportional to the square of that amplitude. So we have one proportionality constant here. Now, this proportionality constant alpha is actually under our control. This is our choice. We've not really said physically what this psi represents. Does it represent energy or electric field or magnetic field? So depending upon what we use to represent the actual amplitudes here, we could get different proportionality constants. So this is our choice of alpha, which really then sets our scale, which is up to us for how we measure the complex amplitudes. Now, there's another proportionality constant that is not up to us, and this is the fact that we associate the brightness actually as being directly proportional to the probability of arrival of the particles. Now, to generate this probability distribution, you recall what is involved as we make this histogram of our different results. We count how many particles land in each bin of our histogram, but then we have to divide by the total number of particles arriving, which is directly related to our brightness. So this proportionality constant for the relating probability and brightness is determined actually by the physics of the problem. That is not under our control. What we do know, however, is that this proportionality to with some proportionality constant to probability gives us the brightness, but we also know that the brightness is related to the proportionality constant, which is under our control, to the square of our wave function or complex amplitude. And since we are free actually to choose alpha, we're going to actually choose alpha so that it actually equals alpha prime, because that's up to our choice. We choose it to be equal to the thing that's determined to us by the physics. The beauty of that then is when we set the same proportionality constant here by our choice of scale of psi, that then leads to a very simple relation that probability is exactly equal to the magnitude of psi squared. No fuss, no muss, no undetermined proportionality constants. From this then finally we determined what this complex amplitude or wave function must be. Basically its intensity, the magnitude of this complex number has to go like the square root of the brightness, and that brightness that we are expecting goes like this transmission function. So it has to, the wave function's amplitude has to be proportional somehow to the square root of this transmission. Square root is time to the 1/2 power. That brings an extra factor of 1/2 into my exponent. So here is my exponent. There's a prefactor here. This prefactor we had determined actually to ensure that when we square psi and integrate it, we get a proper probability that actually integrates to 1. And the last bit of this, of course, is just the phase, which we can copy down here. It's the simple normal-looking phase factor k naught times x, so I have e to the I k naught x. That's what we learned from photoplate 1. On to photoplate 2. The analysis for photoplate 2 all depends upon this idea that we're trying to determine the probability distribution for these momenta along the x direction. But these momenta along the x direction correspond in one-to-one correspondence to the angles of travel of the particles, again through our basic relationship that determines, given the angle and knowing the magnitude of the momentum, we know the x component then of the momentum. And so that then relates in a one-to-one correspondence between the momenta and the angles, and the intensity at the different angles, that brightness number 2 on that photo plate, we know how to calculate from Huygens principle. Huygens principle simply says we have to we calculate the amplitude by superposing the effects of all of these wavelets, and then of course to get a brightness we take magnitude squared, which will then be proportional. The amplitude, final amplitude that we get by summing each of these wavelets, as we sum over the wavelets, we take their initial amplitude and phase at the location of the slit, and then we have to modify it in two different ways as it propagates out to our screen. First, the amplitude decays, and there's a drop-off of 1 over r that we accounted for, and there's also an additional phase factor. Fortunately for the amplitude, we've chosen this to be a semicircular plate, so all of our points are at essentially the same distance, so that can simply come out of the integral and the magnitude squared and just be combined into our generic proportionality constant. So we don't have to worry about the distance. The phase is the only subtle thing about it is now when you look at the geometry, it turns out that the larger x is, you actually have to travel a less distance, and that's why our phase actually turned out to be negative. The magnitude of the phase is k times x again. It's exactly the same mathematics as before, so I'm not going to repeat that mathematics. I will just only copy down the final result here, that this k is p sine theta over h bar, which is really then giving us the x component of our momentum divided by h bar. So once again, we have a one-to-one map between wave vector and the outgoing wave vectors we will just call k, in contrast to the incoming wave vectors k naught, but those just simply map again to the outgoing x component of momentum. So bottom line, at the end of the day here, what we're saying is the probability distribution for the momenta, which we specify in terms of k, but again, k is simply the momenta that we seek over h bar. So we can think of these two things interchangeably, is given simply by the magnitude squared then, it's in proportion at least, we don't know that constant yet, to the integral with respect to x of psi times this negative complex exponential magnitude squared. So that's how we can get the final outgoing momenta distribution. We then actually carried out this particular integral for the very specific case of our given wave function, and we had gone through a somewhat complicated, but not too bad, completion of the square and got to our final result here. So now that we have understood these values, we can begin to think about the interpretation, the meaning of these results. So let's interpret the results. Interpretation. Now, the first thing that we want to look at are actually the general appearance of our results. So what we actually have been trying to understand, the thing which specifies the quantum state of the particle, are these probability distributions. There's the distribution in x, and we get that by simply squaring our wave function, as we had said, right, in the relationship that we have in our nice box here. And then when we take the square of this wave function, where we take first the magnitude and then square it, that gets rid of the phase. And then when we square this, we get back to 1 over square root of 2 pi sigma squared, which is the usual normalization for a Gaussian function, e to the minus, and then squaring this multiplies the exponent by 2. So it's x squared over 2 sigma squared. And then we have just a sort of nice looking probability distribution like so. When we look at the probability distribution for the momentum, or equivalently k, which again, remember, is simply related to the momentum in the x direction over h bar, when we plot that result versus the momentum k, what we find is the square of this function, which will then give us 8 pi sigma squared to the 1/2, times e to the minus, now again I have to double the exponent, 2 sigma squared k, I'm sorry, it's getting a little tight here, k minus k naught quantity squared, which again is a function that's centered on k naught. It's some generic, again, Gaussian shape. It looks something like so. And the interesting thing here that I want you to notice is that the center of this distribution is shifted over by k naught. What this is telling me here is that the maximum, the most likely momentum, right? The most probable momentum that we find. So let's call it that. The most probable momentum comes to us actually as h bar times this k naught, and k naught then is equal to, because k naught is where the max is, and k naught then is the value that we had here. So that gives me p times sine theta naught. So the first thing you notice is that the peak in this momentum shifts around back and forth as I change my incoming angle theta naught, much as we would have expected. The other thing I would like you to notice is that the max occurs, of course, when k naught and k are equal to each other, and the actual value also for k and k naught is, again, k naught is p sine theta naught over h bar, and that then equals k, which is p sine theta over h bar. So the most probable result is also that the angle on the screen, where we get the most brightness, is equal to the incoming angle, just as we normally would have expected, that the brightest spot should be directly opposite the side from the source. Now, that lines up with our intuitions, but this has some really profound consequences. So these are our lessons or our conclusions from this particular analysis. So the first thing that I want you to note is that the probability distribution along x, right, is independent of the incoming angle, the angle to the source, theta naught. It is always just centered on 0. It's just centered where my filter is. But you'll notice the probability distribution for the momenta in the x direction, which is of course the same as this probability distribution in k, right, is not independent. That implies then for us that p of x does not specify, right? There's no way to go from p of x to know the probability distribution for the momentum. And if we can't specify all of the probability distributions, then we also are not specifying the quantum state, not specifying p of x nor the quantum state. So we can't use just probability in x to specify the quantum state. We might also wonder, what about the probability distribution in the momentum, p of x? Now there's another interesting feature here, implicit in everything that we've done. You'll notice that when we calculated this outgoing brightness pattern as a function of theta, upon which our momenta distribution depends, right? I was very glib about where the origin x equals 0 is. I really haven't specified it. That means I could actually shift my slit, if you will. I can shift this Gaussian up and down, and it's not going to affect the distribution along theta at all. That's a basic consequence of the fact that I made the screen very, very far out. So where things land depend upon their momenta, not at the location with which they have passed through my slit. So, in fact, if I were to move this up and down, by a sigma or so, that would not change the probability distribution in the momentum. So this probability is independent of the center location of the Gaussian, of the filter. But clearly, the x probability distribution for the position is not. So, in kind of a parallel way, that implies that the probability distribution for the momentum doesn't, right? It does not specify the momentum distribution in x. Just by looking at it, you can't tell where the slit is, so you can't tell then what the, that's not p tilde. You can't tell then what the position probability distribution will be. And then, of course, nor the quantum state. If you can't get all of the probability distributions for the fundamental variables, you cannot have specified the quantum state. Now, of course, there is something here that does specify both of these probability distributions. We have explicit formulae for them. In fact, I've put those in boxes. If we want to know the probability distribution for the position, we can start with psi and compute that. Likewise, we can do for the momentum. I'd just like to copy it down here in our final conclusions. But if we want the probability distribution in x, that is just equal to the magnitude of psi squared. If we want the probability distribution for the momenta, apart from a normalization factor, which we will learn about later, that is proportional to, actually, I'm going to measure it as a function of k here. K, that is just proportional then to the integral dx of psi of x times this interesting negative phase factor, e to the minus ikx, magnitude squared. Therefore, psi of x specifies both px and the probability distribution in momentum, or equivalently in k, and therefore, thus, the quantum state. So we've done it. We have found actually the minimal descriptor for our quantum state, and it turns out to be this wave function. Our job now is going to be to begin to learn how to work with these various mathematical formulas and to build upon, as our fundamental kinematic variable, the wave function, in order to build up a full description of the types of results we can expect from experiments.